Welcome to the session on the rectangular cavity resonator. We are going to cover the potential functions in the rectangular cavity in this session, as well as the field computation of the modes in the cavity, and we will also cover the quality factor, the stored energy in the cavity. Okay, so let us go to the lecture. So, the first thing we want to understand about the rectangular cavity resonator is derivation of the modes in the rectangular cavity resonator. We did the same thing for the rectangular waveguide. We first of all found out the potential functions for the rectangular waveguide, and from the potential functions we found out the field distributions of the T to Z and the Tm to Z mode sets in the rectangular waveguide. So, we are now going to do the same thing for the cavity resonator, only the fact that is different in this case is that the cavity is the cavity comprises of two shorted metallic plates at Z equal to 0 and let us suppose at Z equal to C. So, the open waveguide structure, if we terminate that open waveguide structure with two metallic plates at Z equal to 0 and Z equal to C, then the propagation along the Z direction stops and we have standing waves along the Z direction. And then we found and thereby we can find the potential functions of this new structure, and from the potential functions of the new structure we can derive the modes of the cavity. So, the first thing to understand is that what are the T to Z and the Tm to Z mode potential functions for the cavity. So, let us now concentrate on the Tm to Z modes of the cavity. So, the potential function psi mnp, where p stands for the eigen value along the Z direction. So, psi mnp Tm can be written as sin m pi x by a sin n pi y by b cos p pi z by c. So, we call this equation 66. So, the question is why it is cos p pi z by c? The reason is, if we look at the electric field distribution of the, if we look at the electric field distribution of the Tm to Z mode, we will find that Ex is equal to Ex is equal to 1 by y cap del square psi del x del z, and Ey equal to 1 by y cap del square psi del y del z. This we derived already. So, both of these have to be 0 at Z equal to C. So, I have the cavity structure, okay. So, this is again my x direction, this is my y direction, this is my z direction. So, this is 0, A, B, and along the z direction okay. So, imagine this to be a, so along the z direction the dimension is C. So, therefore, for the cavity E x and E y has to both vanish here and here on these two surfaces. So, because we have the derivative along the z direction, this derivative operation along the z direction, in order for E x and E y to vanish at z equal to c, we must have this potential function. The other two potential functions are unaffected, because the same boundary conditions as the rectangular waveguide are satisfied by the rectangular cavity. So, these two potential functions are unaffected. So, therefore, this is the potential function psi m n p for the T m to z mode. So, here m is 1. So, here m is 1, 2, 3 etcetera, and n is 1 to 3 etcetera. Okay. And we have the separation equation as m pi by a whole square plus n pi by b whole square plus p pi by c whole square equal to k square. So, let us call this equation 67. Okay. So, similarly for the T to Z mode, so similarly for the T to Z mode, we have the psi m n p T e given by cos m pi x pi a cos n pi y by b sin p pi z by c, which is equation 68. Now, why is this sign? Similarly, if we would look back at the fields of the T to Z mode, we will find E x was given by minus del psi del y and E y was given by del psi del x, and both has to be 0 at z equal to c. So, you see now that there is no derivative with respect to z, there is no derivative with respect to z. So, therefore, the z variation of the potential function has to be sin p pi z by c in order for E x and E y to be 0 at z equal to c. Similarly, the other two potential functions are unaffected, because at x equal to 0, at x equal to a, at y equal to 0, y equal to b, the original boundary conditions for the rectangular cavity resonator are, because at x equal to 0, x equal to a, and at y equal to 0, y equal to b, the boundary conditions for the rectangular cavity resonator is the same as that of the rectangular waveguide. So, here m equal to 0, 1, 2 and n equal to 0, 1, 2. So, here m is equal to 0, 1, 2 and n equal to 0, 1, 2. And the same separation equation holds, which is m pi by a whole square plus n pi by b whole square plus p pi by c whole square equal to k square, which can also be written as omega square epsilon mu, or it can be written as 4 pi square f r square epsilon mu, where f r is the resonant frequency of the cavity. Okay. So, therefore, the resonant frequency is going to vary with m, n and p. So, different modes of the cavity are going to be characterized by different resonant frequencies. So, for distinct values of m, n and p, f r is also going to be distinct. Okay. The resonant frequencies are again independent of whether the mode is T to Z or T m to Z. Okay. So, both T to Z and T m to Z modes of the cavity will satisfy the same separation equation and thereby will have the same resonant frequency. So, the T m n p mode and the T m m n p mode are going to have the same resonant frequency. So, we can from the previous equation write down the expression for the resonant frequency as 1 by 2 root epsilon mu root of m by a whole square plus n by b whole square plus p by c whole square. So, now therefore, once the potential functions are known, we can find out the expressions for the electric and magnetic fields for any given T m n p or T m m n p modes. So, let us consider for example, the T m n p mode. For the T m n p mode given by minus del psi del y, and if A m n p is the RMS amplitude of the psi function, so that can be written as n pi by b A m n p cos m pi x by a sin n pi y by b and sin p pi z by c. Similarly, E y is going to be given by del psi del x, and that will be minus m pi by minus m pi by a m n p sin m pi x by a cos n pi y by b and sin p pi z by c. Similarly, E z will be 0 because it is the T mode. H x will be 1 by j omega mu del square psi del x del z, and that is 1 by j omega mu A m n p minus m pi by a sin m pi x by a cos n pi y by b p pi by c cos p pi z by c. Okay. Similarly, h y can be evaluated to be j by omega mu a m n p n pi by b Similarly, h y can be evaluated to be 1 by j omega mu del square psi del y del z and that is j by omega mu a m n p n pi by b p pi by c cos m pi x by a sin n pi y by b and cos p pi z by c. And h z will be 1 by j omega mu k square minus p pi by c whole square a m n p cos m pi x by a cos n pi y by b and sin p pi z by c, and that can also be written as from the separation equation m pi by a whole square plus n pi by b whole square a m n p cos m pi x by a cos n pi y by b sin p pi z by c. Now, if we specialize for the T 011 mode, if we specialize for the T 011 mode, we will find by substituting m as 0, n as 1, p as 1, just substituting that in the previous equations, we will get E x as pi by b a 011 sin pi y by b sin pi z by c, E y as 0, E z as 0, H x as 0, H y as j by omega mu a 011 pi by b pi by c sin pi y by b cos pi z by c. And h z as pi square by j omega mu b square a 0 1 1 cos pi y by b sin pi z by c. So, from this the average stored electric energy can be evaluated. The average stored electric energy can be evaluated inside the cavity. So, the average stored electric energy will be given by W e tilde half epsilon mod e square triple integral dV. W e tilde equal to triple integral half epsilon mod e square dV. That is half epsilon 0 to c, 0 to b, 0 to a, pi by b whole square, a 0 1 1 square, sin square pi y by b, sin square pi z by c, dx dy dz, and that becomes half epsilon pi by b square, a 0 1 1 square, a b c by 4. And that becomes 1/8 epsilon pi square by b, a 0 1 1 square times a c. So, and you can verify that the average stored magnetic energy given by triple integral half mu mod h square dV is the same as the average stored electric energy in the cavity. So, you can verify that. So, please verify that the average stored magnetic energy is the same as the average stored electric energy. So, now in order to find the Q factor of the cavity, we need to find out the conductor loss, that is the power dissipated on the 6 walls of the cavity. So, for that we find out let us draw the cavity once again. So, now for this structure, power dissipated in the wall y equal to 0, we find that the only tangential component of the magnetic field which is present at y equal to 0, that is the xz plane, is hz. So, the only tangential component of the magnetic field which is present at y equal to 0, which is the xz plane, is hz. So, evaluate hz at y equal to 0, that is given by pi square by j omega mu b square a 0 1 1 sin pi z by c, and P d 1 tilde is given by r 0 to c 0 to a mod hz square dx dz. That is r 0 to c 0 to a pi square by omega mu b square whole square a 0 1 1 square sin square pi z by c dx dz, and that is evaluated to be r pi to the power 4 a 0 1 1 square a c divided by 2 omega square mu square b to the power 4. And an equal amount of power will be dissipated at y equal to b. So, similarly, we can find the power dissipated at similarly we can find the power dissipated at the surface x equal to 0. R 0 to c 0 to b mod h y square plus mod h z square dy dz. Because at the surface x equal to 0, the two tangential components of the magnetic field are h y and h z. And that is equal to r 0 to c 0 to b integral. If I substitute for mod h y square and mod h z square, we will get 1 by omega square mu square a 0 1 1 whole square pi to the power 4 by b square c square sin square pi y by b cos square pi z by c plus pi to the power 4 by omega square mu square b to the power 4 a 0 1 1 square cos square pi y by b sin square pi z by c dy dz. And if I would evaluate and simplify that, this is going to eventually come to r a 0 1 1 square pi to the power 4 divided by 4 omega square mu square b 1 by c plus c by b square. And that is the power, and that is the same power dissipated at x equal to a. So, now for the third surface, power dissipated at the surface z equal to 0, P d 3 tilde is r 0 to b 0 to a h y square dx dy, because at z equal to 0 the only tangential magnetic field component is h y. Okay, h x being 0. So, the only tangential magnetic component remains as h y. So, h y at z equal to 0. So, h y at z equal to 0 is j by omega mu a 0 1 1 pi square by b c sin pi y by b, and therefore, from here P d 3 tilde is evaluated as R 0 to B, 0 to A, 1 by omega square mu square, A 0 1 1 square, pi to the power 4 divided by B square C square, sin square pi y by B dx dy. And that is equal to R 1 by omega square mu square, A 0 1 1 square, A pi to the power 4 by 2 B c square. And the same power will be dissipated at z equal to c. So, from this we are in a position to find the Q factor of the cavity. Before that, the total before that the total power dissipated at the 6 walls of the cavity becomes the total power dissipated at the 6 cavity walls P d tilde, that is equal to 2 P d 1 tilde plus P d 2 tilde plus P d 3 tilde. The Q factor of the cavity is given by omega W e tilde by P d tilde. The Q factor is given by omega W e tilde by P d tilde. So, that is omega W e tilde divided by 2 P d 1 tilde plus P d 2 tilde plus P d 3 tilde. So, this completes the derivation of the Q factor of the cavity, taking into account the conductor loss on the cavity walls. Thank you.